Solving general chemistry problems, electrochemistry. So far we have focused on the benefits of electrochemical devices, power generation, storage, sensors, analytical probes, etc. There is, however, a problematic side to electrochemistry. Corrosion of the structural metals that much of our civilization is built on costs us all billions of dollars annually. In 2014 alone in the US, the cost was almost $750 billion. What can we do about it? A glance at a table of standard reduction potentials points out that most metals, except for the coinage metals such as platinum, gold, or silver, are more negative than hydronium ion reduction and hence are likely to react to form the metal oxides. In fact, most metals are found in nature as their oxide or sulfide ores. With a tremendous energy input, the metals can be successfully extracted, but it should not be surprising to realize that thermodynamically, these metals spontaneously revert to this oxidized state. The fact that we can have metals at all is simply a result of the slow speed with which these oxidation processes typically occur. But the process of metals returning to these oxidized states is what we call corrosion. Finding ways to control and mitigate corrosion is an important goal of electrochemical research. So what are the essential elements of corrosion? Well, there are 5 key aspects with which we can view a corrosion process. As with any electrochemical process, there must always be an anodic region and a cathodic region. These 2 regions must be in electrical contact. They must also be connected by an ionically conducting solution. And there must be some kind of cathodic reactant. Now, there's also an anodic reactant, but that's just the metal which we are observing corrosion in. The anode and cathode regions may be entirely separate and macroscopic in size, or they may be very local to each other on a heterogeneous metal surface. Tiny microcells can arise due to differences in phases in the metal resulting from different heat treatments or from welding. Bending a metal introduces stress that can alter these conditions. There can be natural chemical barriers, such as an oxide layer, or artificial ones, such as paint. Environmental conditions can change along with the local exposure to those conditions, as in the case of road salt spray under your car. The electrolyte itself can be a bulk solution, a boat floating in the ocean, for example, or it can be a nanoscale thin layer of adsorbed moisture from the surrounding atmosphere. A lot of corrosion arises in aqueous environments, but that does not need to be the only one. For right now, however, we will just focus on aqueous corrosion. The anode reaction is always just the oxidation of the metal. However, there are several possible cathode reactions depending upon the pH of the electrolyte and the availability of dissolved oxygen from the atmosphere, and we can observe one or more of these at work. The reduction of hydronium ion can occur in an acidic environment. Oxygen can be reduced in an acidic environment if it's available. The reduction of water to hydrogen gas can occur in a neutral environment, and oxygen can be reduced in a neutral environment as well. So oxygen gas, water, and hydronium ion are all common reagents that can drive the cathodic portion of the corrosion process. The metal cation may remain dissolved in the electrolyte, or, more commonly, it can react to form the metal hydroxides or deposit back as a metal oxide. Notice how the cathode products can be gaseous, H2, or ionic hydroxide. The hydroxide ion concentration will be increasing, thereby increasing the local pH of the electrolyte and contribute to the possible formation of metal hydroxides. More complications can arise. Ions may have multiple oxidation states that can also participate in cathodic processes. Examples can occur with iron or copper, for instance, as shown here. These other states can be stabilized by the presence of other ions. For instance, chloride, which would be present in road salt, can stabilize the copper 1+ state by forming the copper Cl2- ion. Some acids have oxidizing anions, such as nitrate or perchlorate, which can be additional sources of cathodic reagents. An important class of cathodic reagents that we sometimes forget about are microbial infections. You might have, for instance, a water storage tank in soil with the right moisture content. Bacteria such as desulfovibrio desulfuricans are one of the large group of sulfate-reducing bacteria and archaea. These microorganisms breathe sulfate and expel sulfide, which contributes to the corrosion of the iron in the storage tank, forming iron sulfide and leading to hydrogen embrittlement. These microbes introduce additional environments in which corrosion can occur and must be considered carefully. Here's the standard reduction potential table again, but here I highlight the location of the 4 common cathode reagent reactions. Each reaction is capable of driving the oxidation of metals found below it on the table. Remember that these numbers are for reactions at standard conditions and without the consideration of any overpotential requirements. Nevertheless, it gives a good first view of what happens in corrosion and why certain metals corrode under certain conditions while others are resistant. Look at the corrosion of iron. Here is a very simplified example of the processes involved. The iron, as are all surfaces when exposed to the air, is covered with a thin layer of water. A pit has started to form in the steel where the iron is oxidized and removed. This is the anodic region. Somewhere else, oxygen is dissolving in the water. It absorbs on the metal surface along with water molecules, and together they react with a couple of electrons and are reduced to hydroxide ions, which dissolve in the aqueous layer. This is the cathodic region. In the anodic region, iron atoms are competing for electrons with the cathodic reaction, but since their reduction potential is lower, they surrender their electrons and leave the surface as iron 2+ ions. The electrons travel through the metal from the anodic site to the cathodic site. The hydroxide ions formed by the cathodic reaction migrate through the water film to balance the charge transfer and complete the circuit. The iron 2+ ions can then react with the hydroxide ions to form an insoluble iron hydroxide film, which can further react to form a layer of iron oxide or rust. Notice how if we were to somehow keep the oxygen and water away from the metal surface, we could prevent the corrosion from happening. Passivation is the process whereby a protective film is formed, which inhibits the progress of corrosion. For example, we apply paint to a metal surface not only for aesthetic reasons, but also as a protection to prevent or at least slow down corrosion by keeping moisture and oxygen away from the metal. In some cases, the corrosion products themselves can become a passivating layer. A freshly cut surface of aluminum, for instance, reacts quickly with atmospheric reagents to form a layer of aluminum oxide, Al2O3. It becomes a stable layer a few nanometers thick and is bound strongly to the underlying aluminum crystal lattice. It becomes a barrier to further oxidation of the aluminum. By contrast, a freshly exposed layer of iron also quickly forms a layer of iron oxide, Fe2O3. This material, however, is not well suited to remain bound to the underlying iron lattice. The atomic spacings are too dissimilar. Instead, as it grows, it cracks and flakes off, revealing new iron surfaces on which corrosion begins again. Iron rusts destructively because its oxide does not form a passivating layer. Now, this is true of high-strength carbon steel alloys, which have about 1% carbon. On the other hand, stainless steel alloys of iron can develop effective passivation layers. The most common stainless steel is known in North America as Type 304, and is an 18-8 stainless steel, which means it's 18% chromium and 8% nickel. In particular, the chromium reacts with air and quickly forms a passivating Cr2O3 layer. It is self-healing in that a scratch quickly develops a new layer to protect any portion of the underlying substrate. The nickel is also helpful in the corrosion resistance, but chromium is seen as the most significant. Other alloy grades can impart different resistances. For instance, the presence of about 3% molybdenum produces type 316 stainless steel, which is also resistant to strong sulfuric acid solutions, which can degrade 304. A well-formed oxide coating, even if only a few nanometers thick, can still protect a metal from additional corrosion by keeping the cathodic reagents away from any metal. But if that passivating surface is not uniform and free of defects, then the corrosion can continue and we are left with old rusting car bodies and abandoned lots. But iron and all of its steel alloys are by far the most widely used metal in the world. Bridges and buildings, ships and cars, towers and appliances, all kinds of modern things are built from steel. And yet it is the material that does not develop a passivating layer. What can we do to prevent, or at least slow down, corrosion of iron in its many forms? One approach to solving the corrosion problems is called Cathodic Protection. Now here's the same iron substrate with the adsorbed water layer. A cathodic reaction occurs on its surface, extracting electrons from the metal. Those electrons want to be replaced by their neighbors, who in turn need to be replaced, and the domino effect continues until in a nearby appropriate surface region, some iron atoms yield their electrons and are oxidized and leave the iron lattice. Corrosion has occurred. Now, it takes some energy to extract those electrons. This is reflected in its standard reduction potential. What if we could supply those electrons from another source rather than the iron? In cathodic protection, we attach another piece of metal whose reduction potential is more negative than that of iron. That means it gives up its electrons more easily than iron does. Then the required electrons for the cathodic reaction can come instead from this new metal rather than the iron. The new metal is being oxidized and we sacrifice it in order to preserve the steel. What is required is that we have a good low-resistance path for the electrons to migrate. Looking at the standard reduction potential table again, we see that there are many metals more negative than iron. However, the least expensive one turns out to be zinc. A steel-hulled ship, for instance, is subject to corrosion, but bars of zinc metal are bolted to its outer surface. Anodic oxidation seeks to remove electrons from a metal to produce the cation of that metal. Normally this would be the iron that is being oxidized. However, the zinc has a more negative reduction potential, and so it gives its electrons back to the iron to keep it in the metallic state, while zinc corrodes preferentially. The iron becomes a cathode in a cell with the zinc and is protected cathodically. The iron is reduced by the zinc as quickly as it is oxidized by the dissolved oxygen in the seawater in which the ship is sailing. When the ship returns to dry dock, one of the maintenance procedures is to replace the zinc bars with new ones. Bridges, buildings, and pipelines can be protected in a similar manner. They can be attached to the outside or built into the structure and buried in the concrete. A variety of strategies are employed to inhibit corrosion so that these structures can have a long service life. For very large structures like pipelines that span the continent, an impressed cathodic current protection (ICCP) system is used instead. The pipeline is built with a large bed of anodes buried deep in the ground and backfilled with carbon for conductivity. This anode bed follows the pipeline, and a DC power supply is connected at regular intervals between the pipeline and the anode bed, supplying 50-volt bias and 50 amps of current in such a manner that corrosion of the pipeline is inhibited and shifted instead to the buried anode bed. Steel can also be galvanized by dipping a finished piece in a hot zinc bath. A layer of zinc metal crystallizes and binds to the substrate surface. The distinctive crystalline pattern that results readily identifies such material. The zinc layer acts both as a barrier layer and as a cathodic protection layer. Much construction steel is galvanized. Food-grade cans are made from steel and coated to prevent corrosion. Now, our first thought might be that galvanized steel would be a good choice. If the zinc layer develops a pinhole in it, the zinc will preferentially corrode rather than the iron, and the can's integrity is preserved. However, zinc ions are dangerous to human health, so the cans have commonly been coated with a thin layer of tin instead. The tin ions are not harmful to human health, but if a pinhole develops, the iron will rust. Notice how the relative placement of their standard reduction potentials. Now, zinc is more negative than iron and will therefore provide corrosion protection. Tin, however, is more positive than iron and can only provide the protection of a passivation barrier, which is compromised by a defect such as a pinhole or a crack. The can's integrity depends upon the integrity of the tin layer. From experience, most cans are able to be used and stored for a long time before rusting sets in. Many cans nowadays also have an internal coating of a plastic film of bisphenol A, BPA, an organic polymer, to ensure that the food is uncontaminated by the can. There are, however, some health concerns about the consumption of BPA, and its use is being regulated.